Right. So welcome to the tutorials for COMM 298. Before we get into it, just to quickly expand on what Robbie was talking about, tutorials are great because they allow for me to see you guys weekly, to get through the material slowly, really to give you time to absorb the content. Okay. Finance is not an easy topic, right? It's very, there's theory involved. There's a lot of technical things. There's formulas. There's all kinds of stuff that you guys will benefit from learning um, more slowly. Okay, the main benefits, of course, tips, tricks, and secrets for me. How to approach questions. I'll tell you guys if I read a question, how I would tackle it. Um, how to spot, little things that they might be trying to hide in questions. Of course, learning the material early is probably the main benefit of these. Doing well in your exams. Okay, so like Robbie said, I've been doing weekly tutorials for years, and I've found that students tend to do really, really well after joining them. Okay, so I encourage you guys to consider it. Like we said, today's free. Next week is free. We really want you guys to get a taste of it, to really see how beneficial it is, and probably the most useful tool is having access to me, right? By taking the weekly tutorials, you'll have access to me throughout your semester. So if at any point you're struggling, you're stressing out, or you just want more exercises to do, whatever, you can always reach out to me and I'll be happy to help you out. Now, I do like to keep my tutorials somewhat engaging. So I do like to, I do encourage you guys to participate, right? So a lot of times, I'll ask a question to the group and you can use the chat to answer. You can even get on the mics to answer. If you do want to get on the mic, if you want to ask a question, you want to answer a question, feel free to raise your hand. They'll call out your name and then you can just unmute yourself and speak. Okay. Other than that, just try and keep yourselves muted throughout the thing. Bernard, you're asking if it's going to be weekly. How long is each tutorial? It's about 2 hours, give or take, right? Depending on the material. Sometimes we might go a bit over. Sometimes we might finish a bit early, but it's a 2-hour session. So, do you guys have any questions for me before we get into it? Nikolai? So your hand go up and then down.
How do you get such a nice looking beard?
Years and years of practice. Okay. So the plan today, guys, is to get through, is to really focus on time value of money. Okay, so the first couple of chapters in the course, the first one is really an introductory chapter, very basic theory, mainly just definitions, something that you can basically read on your own. So I've gone through the tedious part of reading the textbook, writing the notes, kind of organizing it for you guys. So I strongly recommend you read through this, but it isn't anything that that I can explain to you better than you can just read it yourself. So I don't want to take away good time that we could spend on the more important topic. So we're going to skip over this. This is really for you guys. And we're going to spend today on the material starting where you guys see chapter 5. Now, time value of money is it's the foundation for the next several chapters, right? So in this chapter, we're going to be learning it. This one will feel like a math chapter, right? So we're really learning a brand new form of math, if you will, which will then apply to the chapter on bonds. We're going to apply it to the chapter on equity. We're going to apply it later on to capital budgeting. So this is a really important chapter for COMM 298. You've all been exposed to time value of money before, even if you don't know it, right? If you have a credit card, if you ever taken out a loan, even if you have a savings account, right, where you periodically will go and put some money away, right? These are all real life applications of time value of money, because what time value of money is basically just the relationship between money, time, and interest, right? We know that if we take a certain amount of money, put it away for a certain amount of time with a certain interest rate, that money will grow over time. And that's what time value of money, that's what the entire subject is all about. The purpose of this chapter, what we're going to do together, is really get you guys familiar with all the different time value of money operations, right? So we're going to be calculating things like present values, future values. We'll be doing that for simple things like if I have $100 today, how much will I have in 5 years? And then more advanced ones like if I'm going to receive $100 every year, how much will I have? And it can become more and more complicated. Okay. But before we get into any of that, it's important to understand kind of the basics. And virtually every time value of money situation, no matter what the context is, kind of revolves around these 5 variables. So first you have present and future value. Those are kind of self-explanatory, right? A present value is some value today, whereas a future value, of course, is some value in the future. So for example, if you have $1,000 today and you plan on saving it, that would be the present value, right? And then the amount that it will grow into later on will become the future value in that particular context. And as we work through the chapters, we'll see that in every different context, there's going to be a present and sometimes a future value. Then you have C, which we sometimes refer to as a payment, sometimes refer to that as a cash flow, depending on the context. So this is some recurring amount, okay? And we'll discuss this as we get further into the chapter. But what I want you guys to make a note of maybe for now is that these two are what we call lump sums. A lump sum is simply a single amount, whereas this is recurring. So just to give you an example of the difference, a lump sum would be like you have $1,000 today, you're going to invest your $1,000, right? A recurring cash flow would be like you're going to invest $1,000 every month. Okay, and the moment that the amount is repeating, then we would typically consider that a cash flow. Okay, but again, I'll remind you guys of that a little bit later. T is just the number of time periods. Okay, so again, if you're going to be depositing $1,000 a year for the next 10 years, then you would have 10 time periods. And notice I didn't specifically write years in the definition because a time period could be years, could be days, could be months. Okay. So depending on the context of your question, you would choose your time period accordingly. Finally, you have the effective interest rate, which we use the symbol R. Okay, and that's just the interest rate that we'll be using to calculate whatever it is that we're looking for. And like I said before, basically everything in the chapter revolves around these 5 things. In a lot of the questions, your job will be to find what's given to you, right? Like in the question, they're going to maybe give you the present value, they'll give you the time, they'll give you the interest rate, and you'll be responsible for solving for like the cash flow or the future value. Okay, and that's kind of the idea of most of the situations. And then we'll take that and then apply it to more advanced things later on. Okay, so we'll get through some of the more basic terminology. Of course, we all know what interest is. Interest is the percentage that we apply to our money that really dictates how fast or how slow the money will grow over time. So we know that if we invest our money at 10%, it's going to grow a lot faster than if we invest it at 2% or at 3%, right? But interest, there's a little bit more to know about it. So the way that interest works in virtually every context is interest compounds on itself. Now, you've probably all heard of this before, but it's important to understand the difference between simple interest and compound interest. So simple interest, like the first bullet point says, is just interest on the principal only. Whereas compound interest is interest on the principal plus any other previous interest. So let me draw 2 little timelines just to make sure we get it. And I'm going to be looking in the chat for you guys to help me out. If I have $100 today and I put it into an account that pays 10% simple interest, how much money do you think I'll have 1 year from now? Okay, so looks like everyone is saying 110. That's perfect, right? 110. Because you earned 10% on your principal of $100, so you've earned interest of 10%. A year after that, you'd have 120. A year after that, you'd have 130. Because simple interest is interest only on the principal portion. So every year, you're only going to be earning 10% of $100. Versus compound interest, which is the more common one in real life. So if you were to invest your $100 at 10% compounded, well, the first year would be the same, right? But again, I'm looking in the chat now. What do you guys think would be the interest earned the following year? If my interest is compounding, okay, so one of you has given me the correct balance, 2, 3, there you go, it's starting to come in. You see, compound interest means that I'm earning interest on my previous balance. So $110 times 10% is $11. So now in the third year, I've got 121. Right? If I go one more year, now I'm going to earn interest on 121. So 10% of that would be 1210. And the interest continues to compound on itself. So that's the difference between simple interest and compound interest. Now, in this example, I chose a basic annual compounding, but as we work through the chapter, you'll see that we can compound interest annually, which is once per year. We can compound interest semi-annually, monthly, daily, even continuously. But we'll get to that. Okay. If at any point you guys have questions, again, don't be shy to raise your hand or use the chat. Okay, I'm watching the chat to make sure. Now, some terminology that you guys will want to get used to. I use it a lot. Your teachers will use it a lot. The term discounting, the term compounding. Okay, so whenever I say the word discounting, when you're discounting in the context of what we're doing, you're finding the present value of something. That's what it means. To discount a value means to pull it backwards in time and find the present value of some future value, like in the picture here. You have $100 6 years from now. If you discount that back to today, the present value would be $79.03, right? So this is the present value and this is the future value. So discounting simply means finding the present value. Compounding is the opposite. When you have a present value and you want to find the future value, we refer to that as compounding, moving forward in time. So discounting is moving backwards in time and finding the present value. Compounding is moving forward in time and finding a future value. And this is all done using formulas. Okay. Now, before we get into all the different time value operations that you want to know, all the different formula that you're going to be using, it's important to understand the interest rates. If you recall the first page of the chapter here, I referred to R as the effective interest rate per period. Why it's important to remember that is, in the question, when we give you an interest rate, it's not necessarily going to be the effective rate. Sometimes we'll give you what's called a nominal rate or simply an annual percentage rate or an APR. It's up to you to read the question and know, have they given me my effective rate, or do I need to find the effective rate before I can move forward and solve the rest of the question? So on this page, I've given you the formula you need to calculate your effective rate. Now, what is a nominal rate? Okay, I've written it up here. A nominal rate, or sometimes we refer to it as an APR, stands for annual percentage rate, or QR, which stands for quoted rate. This is simply your interest rate, but your interest rate without considering any compounding. Now, what I mean by that is, and I'm going to use just some blank space here. If I say that I've got an account for you that pays 10% and it's compounded, we use the symbol M, twice per year. Okay, M just means compounding frequency. Okay, I've got that written here. So 10% compounded semi-annually. What that is, so you can visually see it, is taking that 10% and dividing it into two separate interests of 5%. And although it sounds like it's the same thing, it's actually not, right? 10% once a year or 5% twice a year is not the same thing. Or if I say 10% compounded quarterly, now you've taken that 10% and divided it into four separate interests of 2.5%. Again, although all these things sound the same, they're mathematically different. But in both cases, I said it was 10%. So this is called a nominal rate. It's the interest rate prior to factoring in the compounding. The effective rate is the true interest rate. It's the interest rate that does consider the compounding. And you find effective rates using the formula you have on the previous page. And you use effective rates to actually solve time value calculations. You're never using nominal rates in solving time value situations. Very rarely. We're going to do that one time when we're doing bonds next time. But generally speaking, you're always using an effective rate. Now, where it gets a bit challenging is knowing which effective rate you should be using. And this is where you really want to spend a little bit of time wrapping your heads around it. So knowing which effective rate to use depends on the question. Now, when I say which effective rate, I mean that there's an effective annual rate, for example. There are effective monthly rates, effective weekly rates, effective quarterly rates. Sometimes it's totally up to you, depending on the question. And other times there's very specific ones that you need to use. The trick that I use to know what effective periodic rate I need is use your time periods. So for example, if there's a question where in the context of the question, you're dealing in months, for example, you're going to receive $100 a month from an investment. Well, if the time periods in the question is monthly, then you have to use an effective monthly rate to solve it. If the periods in the context of the question are years, right, you're going to save $1,000 a year for retirement. Well, in the context of that question, you need an effective annual rate. Okay, you're starting to see kind of the idea, right? If you're going to make quarterly payments on a loan that you took, okay, to solve that question, you would need an effective quarterly rate. So that's the whole purpose of these formulas. We use the first formula when we're trying to find an effective rate that isn't an effective annual rate. So for example, if you want to find a monthly rate, a quarterly rate, a daily rate, you would use that first formula. The second formula is very specific. It's only used when we're trying to find an effective annual rate. Okay, so that again, so as you're reading through your questions, you read the question, you read the context, you say, oh, okay, for this question, I need an effective annual rate. You'll go ahead and use the second formula. Or, oh, I need a monthly rate. Okay, for that, I have to use the first formula. And we're going to do an example of that. We're going to do a few examples of that anyways. So just to make sure we understand, there's one little remaining variable in this formula, the K. K is the effective period in the question. So for example, if you want to find a monthly rate or an effective monthly rate, you're going to set your K to 12. Okay, I'll write that here. If you want to find an effective, maybe I'll do it this way. If you want to find a monthly rate, your K will be set to 12. If you want to find a weekly rate, okay, you're going to set your K to 52. right? That's how many weeks in a year. If you want to find, and we'll just write one more example. If you want to find a quarterly rate, because that's what you need in the question, you're going to set your K to 4. So let's not mix up K, which is the period, which is the effective period in the question, and M, which is the compounding frequency in the question. The compounding frequency has to be mentioned in the question. It's not something that you can assume. Whereas the K is often what you have to figure out as part of the overall solving of the question. Okay, so I know that's a lot of information to take in at once. So let's try and apply some of this to our first exercise, which you have on the. Yeah, we're going to jump ahead to this page here. We have the first example, lump sum calculations. So this is a pretty basic one. We're going to get into just kind of the simplest versions of these questions, and then as we work through, they'll become more and more difficult. So what we're going to do on this page is go over how to find the present value and the future value of a lump sum. You've got the formulas for that on the previous page. So it says here, Mr. Smith invests $1,000 into an account earning 5% interest compounded annually. So the first thing to look at is always the interest rate. Now, when you're compounding annually, it's the only time that the effective rate and the nominal rate are the same. You're compounding once per year, and 5% is truly 5%. So for the purpose of this question, our interest rate is 5%. Mr. Smith invests $1,000 into an account earning 5% compounded annually. How much will he have in his account in 7 years? Very, very simple to do. When you're trying to find the future value of a single amount, again, we call it a lump sum, you're going to use this first formula, the second one rather. It's the cash flow, whatever it is, in this case, 1,000, multiplied by 1 plus R to the power T. Right, so $1,000 multiplied by 1 plus R, 5%, to the power 7, because it's 7 years from now. So let's all do this on the calculator. We should all get the same thing. According to my calculator, Mr. Smith should have $1,407.10 7 years from today. Okay. Now, other things that you have to know how to solve for example, question B. Now, for question B, there isn't an actual formula. We can make formulas out of it, but a lot of these questions just require some basic deduction, right? So I'm looking at the chat now. Is K 7 in question A? T is 7. T is the number of periods. So in this question, because it's a very simple question in that there's no recurring payments, there's no complex interest rates, we're not using, where is it? We're not using this formula at all. Okay. But if you were to use it, your K would be 1. The reason K is 1, okay, here's a little trick. T helps you decide what your K is. Since T is in years, since in this question, the period of time that we're choosing is years, that means your K is 1 for the purpose of that formula. Just to give you an idea of what I mean, if you look at the following question, where we're going to be dealing in months, okay, then your K and your M will probably change. But for now, again, we're not really worried about that formula. Okay, but that's a trick. If you guys want to write that down, if you're struggling with like, how do I choose K? Okay. Use your use your time period to define that. So if you choose that time will be expressed in months, your K will be 12. If you're choosing for your time periods to be expressed in years, then your K will be 1, and so on. Okay, I'm looking in the chat, see what you guys think. Just based on what we've done so far, how much interest did Mr. Smith earn in those 7 years? Okay, Ria answered correctly. Very good. How about the rest of you? How much interest? And don't worry about getting the answer wrong, right? This is the point of these sessions. Okay, very good. 2 of you guys have given me the right answer. Great. Exactly, right? So very, very, very basic. Mr. Smith had $1,000, put it away for 7 years. Now he's got 1,407. So how much interest was earned? If I take away what I started with, he earned $407.10. I'm asking you how much interest, okay, I want to know in dollars. Some of you guys are answering in percentages. You would probably answer in percentages if I had asked you like what rate of return or something along those lines. But if I'm saying how much interest, I really want to know in dollars how much interest was earned. Okay. Now, what could make this maybe a little bit more challenging is if I asked you how much interest was earned, but not over the entire 7 years, over a specific period. So specifically in the 5th year, how much interest was earned? Now, what you'll notice in finance, the more we work through this chapter and the more you start to do it on your own as well, there's always many ways to get to the correct answer, okay? And there isn't one method that's necessarily better than another. I might show you one method and you might do it differently. As long as we get to the same thing, then generally speaking, all the methods are fine. So I'll show you one way to answer this next question. The important thing to remember is that interest in any given period is calculated based on the balance on the account the period before. Okay, and if you remember when we were doing this example, right? The interest in any given period, like when our balance was 100, we earned 10% of that. When our balance was 110, we earned 10% of that. When our balance was 121, we earned 10% of that. So your interest is always based on the previous balance. Okay, so keep that in mind. So if I'm asking you in the 5th year, okay, so let me draw my timeline. Today is always time 0. This is the end of year 1, the end of year 2, year 3, year 4, and year 5. The question is saying how much interest was earned right here in the 5th year. So Isaac has already given me the correct answer. Very good. So I know that the interest in this year is based on how much money I have in my account right here at the end of year 4. So the first thing I would do is figure out, okay, well, if I invested $1,000 at 5%, so the same formula as before, for 4 years, okay, I would have $1,215.51 right here at this point in time. Which means that in the year that follows, I'm going to earn 5%, because that was my interest rate, of that amount. Times 5% is $60.77 or 78 cents, depending on how you round it along the way. So Mr. Smith, specifically in the 5th year, earned $60.78 in interest. Great. Now, other questions that can come up in the similar context, for example, is solving for time. How long will it take? Can you also calculate the fifth year and subtract from the fourth year? Absolutely. Right. So that's what I was saying before. There's many ways to get it. So you may have calculated this and then also calculated the balance here and found the difference, right? And you would have got to the same answer. Both are 100% correct. One method is not better than the other. So now if we're trying to solve for time, right? In this following question, we're saying, how long will it take for Mr. Smith to double his money? Use the same formula, but now we're asking you, if he's starting with 1,000, the interest rate is still 5%. We don't know time, right? Because we're saying how long. And we want to get to 2,000. Now this one requires a little bit more as far as the math goes, right? A bit more mathy. So if you're comfortable with the algebra, you guys can already start it. You can put your answer in the chat, but I'll walk you through it. The important thing is that you knew how to set it up. I just want to double my money. Hey, yeah, so today's session will be recorded and sent to you guys. Okay, so the first thing, of course, would be to isolate my bracket. So let me get rid of my $1,000 on both sides here. Okay, that'll get rid of it. So now I've got 1.05 t equals 2. Now using logs, you want to isolate t. So I don't know how long ago you guys did logs, but the idea is you put a log in front of both, you can bring down your exponent. I'm sure that rings a bell somewhere. So now this equals t multiplied by the log of 1.05 equals the log of 2, which you could then continue isolating. The log of 2 divided by the log of 1.05. Now we go to our calculators and punch this in. So a lot of you guys had already chatted to me, 14.21. That's perfect. It would take roughly 14.21 years to double your money. Right. Finally, the last part of this question is to show you guys what to do in the uncommon question of compounding continuously. I say uncommon because in reality, in real life, there's hardly ever any situations where things are being compounded continuously, but you still need to know it for the purpose of the class. I've given you the formula here, right? I'll just paste it over here. When you want to find the future value of something that's compounded continuously, you just want to follow exactly this. So how much would Mr. Smith have in his account in 7 years if it was compounded continuously? I'm still starting with 1,000. I'm going to multiply by e, right, the exponential variable, to the power r, which is 5%, times t, which is the 7 years. You just punch it directly into your calculator. Everyone's calculator should have the exponential variable. I got 1,419.07 if I round it. Remember, guys, don't get too comfortable with this formula in the sense of using it loosely, right? It's very specific. You can only use this if I specifically say compounded continuously. Okay. So let's do another example. Mrs. Brown received $5,000 for an investment she made 5 years ago. If she earned a return of 6% compounded monthly, how much did she initially invest? I'm asking you for the present value in this case, right? If I have $5,000 now, how much did I invest 5 years ago? So the first thing I'm noticing is that they told me my interest is being compounded monthly. So my M is 12. If you're trying to find the present value, it's basically the same thing, right? We're going to be taking the cash flow, and instead of multiplying it by 1 plus r to the t like we did before, you're just going to divide it, right? If you multiply, you're going to compound and move forward in time. If you divide, you end up discounting and moving backwards in time. So here's my timeline of 5 years. If she's got $5,000 today, how much did she invest 5 years prior? And again, remember, there are many ways to get to the right answer as long as you do everything correctly. So $5,000 divided by 1 plus, now we need the rate. I'm looking at the chat for you guys to tell me what you think I should do for the rate. Okay. So one of you said just take the 6% and divide it by 12. Another student said 6% because it's monthly. Okay. Now, maybe the wording, sometimes the wording throws you guys off. If I see 6% compounded monthly, that doesn't mean 6% per month, okay? The correct way of interpreting that is 6% is always an annual rate, compounded monthly, divided into monthly periods. So this would be the quickest way to deal with the rate. Can you always just divide? No, right? Once we get to the more advanced questions, you'll see situations where you can't do this. But because this is still a simple question, where there isn't anything more than just a lump sum going on, you can keep it simple and divide your rate. So this becomes 0.005 per month. But if you do that, then your T should be what? Looking at the chat now for you guys to tell me what you think. What do you guys think I should plug in as T? Okay, exactly. Since you chose to use a monthly rate, right, per month, your T has to be in months as well. So 5 years is 60 months. So 60. Okay, really important. If the R is monthly, the T is monthly. If the R is daily, the T is daily, right? If the R is annual, the T is annual. Okay, let's just punch that into our calculators. We should get 3706.86. Great. Okay, so I want you guys to try the next one on your own. Shouldn't take you more than a minute. How much was the value of the investment at the end of year 2? Basically right here. I want you guys to write me the answer rounded to 2 decimal places in the chat. Okay, still waiting. So remember, we determined that Mrs. Brown invested $3,706 initially. I'm asking now the value of the investment at the end of the second year. So if she started with this much, now we're trying to go forward in time again. We're compounding again. We're going to multiply by 1 plus the rate, just like we did in the previous question, to the power 24. Why 24? We're trying to move forward 2 years, but in months, right? So that should give you $4,178.22. If you got a smaller number than 3,706, maybe you divide it again, right? Maybe you went even further back in time, which isn't what the question asked you, right? It asked you, what was the value at the end of the second year? Okay. So that's that. Now, what do we think of this question? If you had initially invested 4,500, what effective annual rate of return would she have earned? So let me draw this one out. What if she initially invested 4,500, ended up with the $5,000 that they told us 5 years later? So what are we solving for here? Which variable? Good, right? So two people have said R. Exactly, right? We're solving for the rate. Cool. Same formula. We're starting with 4,500. 4,500 times 1 plus the rate. Oops, no, that's wrong. I'm looking for the rate. 1 plus R. Since it's asking for the annual rate is T5. Exactly. So that's an important thing to notice, right? Because we asked you for an effective annual rate, not an effective monthly rate, we're going to set our T to 5 so that it's in years. And by setting that to 5, you're going to get an annual rate when you solve for R. If you were to set that to 60, then you would end up with a monthly rate, and then you would have more steps to take to get to an effective annual. So it's important to read the question and to spot all these little shortcuts, right? And that has to equal 5,000. And then again, you just want to isolate for R algebraically. This one's a little bit easier. It doesn't require any logs. So you guys can start solving that. I'll do it at the same time. All right. So now I've got 1 plus R to the 5 equals basically 1.111. And we keep reducing it. So if I do the math here, we should all get to 0.0213 or 2.13%. So whether it's R, N, future value or present value that you're looking for in these situations, you're basically doing the same formula, just isolating for a different variable. Okay. Do you guys have any questions about what we did on this page? Right. So let's start talking about, will we do anything, any questions using K? Yeah. So what you'll notice is I didn't use K in the last two questions because I didn't have any payments, right? When you don't have payments or when you don't have recurring cash flows and you just have single cash flows, the questions are much simpler. The moment you start to deal with annuities, that's when K really starts to matter, right? Where you have payments that are repeating. So yes, we're going to see a bunch of those, don't worry. So the most common type of recurring cash flow is called an annuity. Okay, an annuity has specific characteristics. They're listed here, and you have a picture of it right here. For something to be considered an annuity, there has to be a constant payment. So in my picture here, it's $100. You see, the amount of the payment has to be the same. The discount rate or the effective rate should also be the same. During this 6-year period, the interest rate was 6% and it didn't change. The time between the payments should also be constant. If it's 1 year between payments, it has to stay 1 year between payments. And finally, there has to be an end. The payments, the number of payments is not infinite. It has to be finite. It has to end at some point. If you're solving or if you're reading a question and all of these characteristics are met, you're dealing with an annuity. Okay. And to find the present value and the future value of an annuity, first let's talk about what it actually means, right? Now you've seen present value, you have the general idea, right? The present value is just the value today of some future amount, right? So let me zoom in a little bit here. If I tell you that I'm going to give you $100 a year for the next 6 years, and I say, well, what is that worth today? We've learned now how to find the individual present values of each payment, right? Using our basic formulas from the previous page, if I said $100 in 1 year, that would be worth 94 today. $100 in 2 years would be worth 88 today, and so on, right? But it would take forever to solve that question in this way. What if there was 20 payments? What if there's 100 payments? So of course, we're not going to do it that way. To find the present value of all the payments in one shot, or to find the future value of all the payments in one shot, you're going to use these two formulas. The first is to find the present value of an ordinary annuity. The second one, of course, is to find the future value. They look almost the same, so make sure you spot the differences. So we're going to, I'm just going to copy these, bring them down with me to the following question. So let's do our first exercise on that. An investment will return $600 at the end of each year for the next 7 years. The appropriate discount rate is 5%. What is the value today of that investment? So what is the present value, in other words? Could I give a real life example of an annuity? I can give you tons, okay? If you take a car loan, right? You want to buy a new Tesla, you take out a loan of whatever it costs, right? 100,000, let's say. That's an annuity. Why? It meets every characteristic. You have the payment is the same, right? Let's say your payment is $700 every month. So equal payment, equal time between payments. You're going to have a payment every month. The payments are not going to go on forever, right? They only go until you've paid off the car. And the interest rate stays constant the entire time. See, a loan, most loans are annuities. Or you say, you know what? I want to save for a vacation. So every month, I'm going to put $100 into my bank account, right? So you've got an annuity, equal payment every month, and your bank account's interest rate generally stays the same. So that would be another example. Do you know if we're allowed formula sheets, or do we have to memorize all the formulas? That kind of varies every semester. I would presume that you can have a cheat sheet, but you're going to want to definitely confirm that with your prof. Okay, so we're going to use this formula here. If I want to find the present value of several recurring payments or of an annuity, my prof said formulas are given. There you go. So you'll be given formulas. The C you have here in the formula is the value of one payment. So in our example, the C would be the 600. So if you're going to have $600 cash flows, 1 over the rate. Here they've given you the rate. Look at the wording, okay? And this is what I was saying earlier. It's important to know when I've actually given you the effective rate or when you have to find the effective rate yourself. In this question, we said the appropriate discount rate is 5%. They're giving you R. Don't break your heads looking for it. It's right there. For a second, compare that to how it's worded here. The account is earning 8% interest compounded daily. Here, it wasn't given to you. By giving you this information, we're saying, okay, this is the nominal rate. This is the compounding frequency. You have to find the effective rate. So you're not necessarily always going to have to find the effective rate. You see in this question, it was given to you. And after practicing a bunch, you'll see the patterns of how they present the information to you. So in this case, the R is just 5% minus 1 over, just following my formula, R times 1 plus R to the power T, which is 7 years. So let's try to punch this in. So let me see in the chat what you guys got, and we'll compare with mine. So I got 3,471.82. Let me know if you got the same thing. Right? Make sure that if you're clicking yes, it's because you actually did it and you're not just agreeing with me. I often screw up on the calculator, right? Okay, it looks like you all got the same thing. That's very good. Cool. Right, exactly. So that's it. If you're going to get $600 at the end of each year for 7 years, the present value of all that is 3,471. But what if I said that the first payment was to be received today? You compare, before I said that the payment is to be received at the end of each year for 7 years. When a payment is received at the end of a period, we call that an ordinary. So this first question that we solved is called an ordinary annuity. When you're reading a question, if I don't specify the timing of the payment or the timing of the cash flow, you always assume that cash flows take place at the end of each period. Because by default, everything is ordinary, okay? There are, again, uncommon questions, but they can ask you a question where the payments take place at the start or at the beginning of each period. What tells me that it happens at the beginning of the period here is I'm saying that the first payment was received today. I want to show you what that looks like on a timeline. Today is time 0. So if you were to get your first payment today, and you were to still receive 7 payments in total, this is what your timeline looks like. So you see, the payments are received in this question at the beginning of each period. So at the beginning of year 1, which is today, I got my first payment. At the beginning of year 2, at the beginning of year 3, and so on. We call this an annuity due. Just to make sure we understand the difference, if we were to contrast that with your typical cash flow, let me just cheat a little bit. Okay. Normally, this is what cash flows look like, where the payments take place at the end of each period. What I'm saying is, what if they weren't, right? What if they were received at the beginning? So very, very easy to solve. Here's a trick. The present value of anything that is due is equal to the present value of the ordinary multiplied by 1 plus the rate. So you would still do it the exact same way, right? You would just have an extra step. Like you would find the 3471.82. You would then multiply that by 1 plus the rate, which in this case was 5%. And you would have 3,645 and 41. So really, it's easy to do. The important thing is just that when you read the question, you spot where they specifically say that this is an annuity due. And the way we said it was that the first payment was received today. While you're at it, you can even write that the same rule applies to future values, if ever. The future value of anything due is equal to the future value ordinary, again, times 1 plus R, okay? Same trick. So let's do another example. You plan to save $1,000 at the end of each. Oh, okay, we're missing a word here. So at the end of each, let's say month. Yeah, let's make it interesting. At the end of each month, into an account earning 8% interest compounded daily. So this is the first time we're going to really have to start worrying about the interest rate. We told you, first of all, that the interest rate is compounded daily. So M is 365, right? There are 365 days in a year. But Because your payments are made monthly, that means that your T is going to be in months. Which means your K also has to be in months. So before I do anything in this question, I have to find my monthly rate. I can't solve this question without my rate. So let's put all that together, right? The M365, that's just given to you in the question, right? But to know that K is 12, you have to look at the rest of the information. Look at the payment frequency. You're making monthly payments, which tells you that your T, when you get to that point of the question, will be in months, which tells you your rate should be in months, meaning K would be 12. So 1, now I'm just using the formula, right? 1 plus the APR, which is 8%, over M, which is 365, to the power M over K minus 1. This is going to give you your effective monthly rate. You should get 0.00669. Doesn't the compounding have to be in months to agree with the time period? No, so that's actually a good point to bring up, okay? Your compounding periods and your time period in the question don't have to be the same. And that's what makes that's what you have to keep track of, right? I could have monthly payments, like in this question, but have interest compounding daily, annually, quarterly, right? Because it's two different things. Compounding frequency and payment frequency. Those two can be the same in simple and simpler questions, but they can also be different, like in this question. So it's very important to not think that those two necessarily have to be the same. Okay, and you never have to really assume the compounding, right? That's the one that's given to you. So here, this is my monthly rate. This becomes the R basically in your question. Now we can start solving properly. How much will you have in your account at the end of the 4th year? So now we're looking for the future value. So for that, I'm going to take our formula from before. This time we'll take the future value formula. Just going to bring it down. Same concept. The cash flow is 1,000, right? That's how much money will be periodically deposited times 1 plus your R, 0.00669 to the power T. Now T is what? I'm looking at the chat. What do you guys think T should be in this question? Everyone is saying 48. Very good. Remember, it's 4 years, but it's in months, so 48 minus 1, 0.00669. There you go. Oh, my thing froze. Second, why is that? Hold on, oh, there it is. Okay. So again, I got 56,382.28. Let me know if you got the same or different, right? If you got different, click no. Maybe I got it wrong. Okay. How do you know when to solve for the effective monthly rate versus just dividing? That's a good question. So when your M does not equal your K, okay, like in this case, right? You have to find the effective rate with the formula, okay? If they're equal, you can just divide. If you want a little trick, if M and K are the same, then just divide, right? You don't have to use the formula. You could, you'll get to the same answer, but it's just faster to divide. But if they're not the same, you absolutely need to use a formula to find the effective rate. Okay. Question B says, how much will you have in your account at the end of the 4th year if the first deposit was made today? See, again, we're saying if the first deposit was made today, which means now we're saying that this becomes, once again, an annuity due. But based on what we said earlier, all you would do is take your answer from when it was ordinary and multiply it by 1 plus your rate. And it would be just slightly higher, right? So 56,759 and 48. Rose again. Okay, so my screen should come back to. Okay, while my screen loads, I got 56,759 and 48 cents. I'm assuming, oh, there it goes. That we all got the same. Sorry, guys, this disconnects sometimes. There it is. Okay, very good. Cool. Now let's talk about, is the formula FV due equals FV ordinary times 1 plus R then? Yes, exactly. Same rules. Whether it's future value or present value is the same. Okay, we've seen annuities. Now let's talk perpetuities. A perpetuity is an annuity in every way, same characteristics. The only difference is that it goes on forever. Real life example of that could be one of those lottery tickets where like you win $1,000 a week for the rest of your life, right? In theory, that's an infinite, doesn't mean you're going to live forever. But when you win, you don't know exactly how many payments you're going to get. In theory, from that point on, the end is undefined. Okay. Another real life example of that we're going to see later on in the semester is a stock. When you buy a stock of a company and that company pays dividends, in theory, that stock will continue paying you dividends for as long as you own it. So it's got indefinite payments or infinite payments. Never really hard to know that you're doing a perpetuity because they have to tell you that the payments go on forever. And the formula is super simple. That's all it is. The present value of a perpetuity is the cash flow, right, divided by the rate. Notice that there's no t because it goes on forever, so there's no time. There's no future value, again, because there's no end. It goes on forever. So really, when it comes to perpetuities, all you're really finding is the present value. If it's a perpetuity due, it's the same thing. It's the ordinary multiplied by 1 plus r, the same principle as before. Now, although it may seem a little hard to wrap your heads around, we are able to find the present value of something that goes on forever. Here you have an example of it. $100 a year forever at 6% interest is worth $1,666.67 today. So let's do an example. Now, what's important to remember, guys, is that all the rules that we're learning about interest rates always apply. About like effective rates, Ks and Ms and all that. Never forget that. So let's read this question. You just won a lottery that will pay you $5,000 at the end of each month forever. There you have your perpetuity. Someone is offering to buy the ticket from you for $1 million if the interest rate is 6% compounded weekly. Now I need your help. What's my M? What's my K in this question? Looking in the chat for you guys to tell me. Okay, like 5 of you have answered. Very good. What about the rest of you? Okay. So compounded, which is M, 52, compounded weekly. K, right? You have to look at the payments. Because the payments are received each month, your K will be 12. So because they're different, before I do anything, I'm going to find my monthly rate. Again, monthly, it's not always monthly, it's been monthly for 2 questions. Monthly because my K is 12, right? So 1 plus the nominal rate over M to the power M over F, over K rather, minus 1. You should get the 0.005. I mean, if you keep more decimal places, you'll eventually get to that, but always the more you keep, the better. Okay, so we've got our monthly rate. So now if you want to find the present value, all you would have to do is follow the formula. The cash flow, the recurring cash flow, the recurring payment is 5,000, and the rate you just found was that. And this is why rounding is important. Depending on how many decimals you round it to, your answer might change slightly. Like I actually kept all of my decimals and I got this answer on my calculator. So this would be the most accurate answer. If you're off by a little bit, I can't imagine it mattering, especially if you kept 5 decimal places, then you're good. Okay. So what we found is that this lottery ticket today actually has a value of 998,000. Somebody's offering you $1 million. So you should sell. Because they're offering you more than the value of the lottery ticket, more than the value of your winnings. Well, what if the payments, what if the first winning was received today? What would I do? So I'm looking at the chat for you guys to tell me, right? If we received our first $5,000 today, rather than at the end of the month, exactly, Nikolai is saying, take the answer from before, multiply it by 1 plus your rates, whatever it was. And now you should get 5,000 more, which would be 1,003,078,89. Again, depending on how you round it, it'll be a little bit different. And exactly, right? Like some of you guys are saying in the chat, now you wouldn't sell. Because the value of your ticket in this scenario is higher than the 1 million. Okay. Okay, very good. So now again, let's turn the dial a little bit more and start dealing with slightly more advanced types of cash flows. Okay, so we've seen annuities and perpetuities now, where the payment was the same every period, right? Let's talk about growing annuities and growing perpetuities. Now, these still follow the same, they still have the same characteristics as your typical annuities, typical perpetuities, except for the fact that the payments are increasing, right? In every question we did so far, the payments are the same. But what if the payments were to grow every period, right? So we're introducing a new variable called the growth rate, and you'll see it in the formulas. The growth rate is the percentage increase or decrease of your payment each period. For example, I'll give you $100 next month, and then every month I'll actually give you 10% more. So your payment, your cash flow is not staying constant, it's growing. It could also be shrinking, right? I'll give you 2% less, for example. This is very common in stocks with dividends. The formulas are kind of intense. Well, the first one anyways, the second one's not so bad. So when you're trying to find the present value of a growing annuity, you've got this wonderful thing. So let's give it a shot. The important thing is you're reading a question and you know from the context to use the formula, because using the formula is just using a formula, right? I really want you guys to read the questions and be like, okay, based on what they're saying, this is an ordinary annuity, or this is a growing annuity, or perpetuity, or whatever. You just lent your sister money to pay for a new car. To repay you, she's going to give you 10 annual payments. But what I know so far is that I've got 10 payments and they're annual. So I know that my K is 1. The first payment 1 year from now is $1,000. Each payment after that will grow by 5%. There's your growth rate. Each payment will grow by 5%. And the discount rate, the R, is 7%. How much did you loan your sister today? In other words, we're asking you what the present value is, right? How much did you give your sister today if she has to give you back these payments for the next 10 years? So let's punch it in. Now, when you're solving this, the C in the formula is always the first payment. Now, it's important to remember that, right? In the other questions, it didn't matter. They're all the same. But when you have growing payments, you're always plugging the first one. So that would be the 1,000. So 1,000 multiplied by 1 over, now it's just formula. The rate is 7. The growth rate is 5 minus 1 over this again. This time, this one is multiplied by 1 plus the growth rates over 1 plus the rate to the power 10. Okay, so my thing is just lagging behind a little bit, but in a second you'll see it. There it goes. Okay. Again, sorry about that. I don't know why this is happening. Maybe my computer's getting tired. Okay, so there. Okay. So if you guys have chatted the answer to me, I got the same thing as you, 8597.63. Present value, the amount that you lent your sister today, is 8,597 and 63 cents. Okay, so as we finish writing that up, are there any questions about this new type of cash flow? The big giveaway, of course, was the growth rate, right? Each payment after that will be 5% higher. There's a typo there. It will be 5% higher. Okay. Take a look at another one. Mr. Nichols wishes to start a fund to give a scholarship to one student per year at his old university. The first scholarship is expected to be paid out a year from now and will total $40,000. If Mr. Nichols wishes the scholarship to increase by 2% per year to offset inflation, how much should he donate today? I should say if the appropriate APR is 4% compounded daily. Okay. Now I'm looking at the chat for you guys just to give me pointers here, okay? What's the very first thing I should do in this question? How would you approach this? Good, right? So Nikolai and Nicole both said that we need to deal with the rate first, right? Okay. So I need M and I need K. Help me out. So M is 365. Very good, right? We said it here, compounded daily. Only one of you has given me K so far, though. So if the scholarship is going to pay out annually, so once per year, your K is 1. So I need an annual rate. 1 plus my annual percentage rate of 4% over 365 to the power 365 over 1 minus 1. Yeah, our annual and EAR are the exact same thing. That's why you don't really need that second formula on that page, right? Because they really are identical. Can you go over how you determine M and K? Sure. So M is given to you in the question always, right? Compounded daily, that's my M. M is your compounding. The K is determined by the frequency of the payments. Because he wishes there to be a annual scholarship, which means that once a year we want to pay a student a certain amount of money, K is, our time rather, is expressed in years. So that's K, right? If your time is expressed in years, you should set K to 1. If your time was expressed in months, like in the previous questions, your K would be 12. So now if we punch this into our calculators, you'll get something like 0.04081. Okay. From this point, it's just choosing the right formula. Because he wants the scholarship to go on forever, right? We didn't say anywhere in the question that he only wants to give a scholarship for a certain number of years. He wants there to be enough money so that there's a payment each year, and we want each scholarship to be 2% higher than the previous year. So what do we have? We have our rate. We have our growth rate. We need it to grow by 2% per year. So the formula for the present value of a growing perpetuity is very basic. It's the first cash flow divided by R minus G. That's it. Cash flow over R minus G. And you should end up with a fairly large number. Right? Something along the lines of 1,922,152.81. Again, depending on your rounding, maybe it's a little bit different, but that's basically it. So what this is telling me is if this person gives the school $1,922,000 today, then for the rest of time, There's always going to be money to give a student a scholarship. And every year that scholarship will increase by 2%. The money will never run out. Now let's talk about something a little bit different. Well, same, but different. Something called a delayed annuity or delayed perpetuity. Delayed annuities or delayed perpetuities are simply annuities or perpetuities that don't start immediately. Like if you look at the picture here, right? Here you've got a 3-year annuity, but only starting in year 4, rather than starting right away. So I want to show you guys how to solve this. Basically, you've already learned how to do it. It's 2 different formulas we saw. We're just going to put them together. You see, it says in the picture what to do. The first step is always dealing with the annuity and then taking the present value that you find and discounting it back to the present day. So it's always a 2-step process, okay? We're going to do that in the example on the next page, so you'll see. So anytime that the annuity or the perpetuity starts in the future, remember, it's always going to be a 2-step process. So let's take a look at this. Mr. Brown has a 14-year-old daughter that already has dreams of attending Harvard University. Mr. Brown expects to need $50,000 at the end of each year for 4 years to pay for his daughter's tuition. He expects to make the first payment in 8 years. So let's start drawing the timeline here. Today is here. 1, 2, 3, 4, 5, 6, 7, 8. He's going to make his first tuition payment here and then make 4 payments in total. So this is our timeline. Right here, 8, 9, 10, and 11. So it's an ordinary annuity. It's just starting in the future. The appropriate discount rate is 6%. So they've given you the R. How much should Mr. Brown save today to have enough money to pay for his daughter's education? We're asking you for the present value today at time 0, which I call PV0. Okay. So of course we can see in the timeline, this is a delayed annuity. It's an annuity starting later on. Step 1. Find the present value at whatever time or wherever the annuity actually starts. So using what we've learned, this is an ordinary annuity. Okay, so now we have to think back to how we found ordinary annuity present values, right? It was the cash flow multiplied by 1 over R minus 1 over R times 1 plus R to the T. It was like one of the first formulas we saw. Okay, let me just go back and point it out in case I wrote it wrong too. No, further back. This one here. So here we are. So since my first tuition payment is 50,000, that's what I'm going to plug in as C. And you see, we're solving the first part normally as if this were the entire question. So 1 over the rate minus rates 1 plus the rates to the power of 4, because there are 4 payments in total.
Mama, oh, şunu.
So for this first step, you should get 173,255 and 28 cents. Now, this is not the final answer, because although it is a present value, it isn't the present value at time 0. What you have to understand, especially for delayed annuities, is that whenever you're calculating a present value, okay, on your timeline, that present value is always one period before the start of the payments. So because the first cash flow took place at time 8, this is the present value at time 7. Okay, the present value is always one period before the first cash flow. So Mr. Brown has to have $173,000 at year 7 to pay for his daughter's tuition. But that's not what I asked you for, right? I said, how much does he need to save today? So your second step is to take whatever present value you found and bring it back to time 0. So now I'm asking you to do basic discounting, the first thing we saw today. So you're going to take your 173,255.28 divided by 1 plus R, the R was 6%, to the power 7, because you're trying to go from PV7 to PV0. Then you should get something around 115,224.66. And that's your final answer. In order for him to have this money in years 8, 9, 10, and 11, he needs to deposit $115,000 today, let it grow for 7 years, and then he's going to have just enough to pay for all those tuition payments. So the important is the 2 steps. Okay, so again, any questions about how we did this? All right, so let's do another one. An investment will return $1,000 at the end of each year for the next 4 years. The returns will then begin to increase by 4% per year for the next 10 years. The appropriate discount rate is 7%. So this is not so much a delayed question, although there is that element in it. This is what I typically like to refer to as complex timelines, because they're timelines or cash flows that change. Every question we've seen so far has been just an annuity or just a perpetuity. But what if I tried to complicate that and I gave you something like this question, right? Where it says you're going to get $1,000 at the end of each year for 4 years. And then after that, the returns are going to increase. So after this, it's going to increase by 4% for the next 10 years. So years 1, 2, 3, and 4, the payments are the same. But then years 5 through 14, the payments go up by 4%. When you get a question like this, and again, this is going to happen more in the chapter on stocks, but it's important to understand it from now because the way to solve this is using the stuff you already know. Whenever I have these complex timelines, I like to divide them and work with them separately. I found that this is the easiest way to tackle them rather than try and combine them. So I want to show you guys how I would solve a question like this, and you should always use pretty much the same method. Now I'm looking at the chat. I want you guys to tell me what you think. Okay, the first 4 years, how would you define that cash flow? What would you call that? Exactly, right? This is an ordinary annuity. Cool. How about the right-hand side now? What would you call that? Growing what? Don't just say growing, but growing what? Is it growing forever? Ah, okay. It's not growing forever, right? It's growing for 10 years. This is a growing annuity. So this is exactly, if I were a student, this is exactly how I solve this question. I draw my timeline, I chop it up, and I would label it. Why do I label? So I don't have to break my head thinking, okay, well, how am I supposed to solve this? There's a formula for ordinary annuity. There's a formula for growing annuity. The ordinary annuity is basic, starting right away. And the growing annuity is delayed because it doesn't start until year 5. So think of this as two completely separate questions. We're going to solve them separately. And at the very end, we'll add the two together. Okay? So let's see how. Ordinary annuity, same formula as before. Present value is equal to the cash flow multiplied by this whole thing. So, oops. So the present value, the first cash flow is 1,000. The rate is 7%. And this portion of my timeline only has 4 payments. So I've taken into account those 4 with my first calculation. Do we solve more present value than future value normally? Yeah, in general, in this class, present values are almost always what we're looking for. That's why you don't see that many future value formulas. Okay. Okay, so let's punch it in. All right, whenever you guys have it, let me know what you get. Okay, very good. So some of you guys have already started sending the answer to me, 3387 0.21. That's good. And you see the first section of my timeline is complete. Now let's go to the right, okay? Same concept as what we did before. This is a growing annuity. So there's a formula for that, and it's delayed. So there are the two steps, okay? So I'm looking in the chat, okay? What should I do first? Well, what should I do first? How would I find the present value of a delayed growing annuity? Get PV5, then make it PV0. Okay, you're 99% right. You're both saying PV5, but will it actually be PV5? PV6? No. PV4. Okay. Remember the rule. The PV is always one period before the start. So because your growing annuity starts here, you're going to find PV4. Okay, super important. Now, before any of that, I need to find my cash flow in year 5, right? Like, what is this payment? How much is it? Well, it's 4% more than the previous one. Okay, so 1,000, if I increase that by 4%, my first payment there is 1,040. My first cash flow. And then we've got that mega formula that I can never remember by heart. This thing. Copy. Yeah, this thing. So the first cash flow of this portion of my timeline is 1,040. 1 over R, which was 7%, minus G. So they said the growth rate from this point on would be 4%. There's no way this fits. Hold on. Okay. Minus, again, 1 over R minus G times 1 plus G over 1 plus R to the 10. And then close the bracket. Okay. So go ahead and punch that in for me. $85.80. Bernard, I see your question. I'm gonna just take a look in just a second. So 85.80.65. Okay, so Bernard, you're asking why are we not using the same formula in the Harvard University problem? Because in the Harvard University problem, the tuition payment stayed the same. So this was a delayed ordinary annuity. This is a delayed growing annuity because the payments are growing. You see that? Cool. All right, PV4. Now, how do I turn PV4 into PV0? discount it. Exactly. Your basic discounting. So 8580.65 divided by 1 plus the rate to the power 4 is 6546.14. So 2 separate questions, basically, until the very end. Now that everything has been discounted, you can add your 2 numbers together. The present value of this entire timeline is the sum of the individual present values of these sections. And as long as you keep this method of like splitting them up and doing them separately, no matter how complex we can make it, you'll have no problem solving it. Because you don't have to worry about how complex it is. You're just solving 2 questions. Okay, so it's just about the time to end. So we're going to continue this chapter at the beginning of next class. Remember, guys, that next week is also free. You guys should all attend. And please do invite your friends. The more people we get into this, then the more likelihood of us continuing to do it, of course. It would also be great, in the chat, I'm putting a link to just a little quick survey. If you guys don't mind doing it, it shouldn't take more than a couple of minutes, just to kind of tell us about what you thought about today and how it went. And so, yeah, so next week we're going to continue with this, and we're going to also start the chapter on bond valuation. Okay, so we'll be finishing off loans, and we'll discuss bonds as well. The recording, guys, you should receive an email tomorrow with the recording. Like Robbie said, we don't typically give out the recordings for security reasons, but since today's a free session, they're going to make an exception. So I guess tomorrow you'll get an email with a link to the recording. All right. And for those of you that don't have it, remember, by doing the weeklies, you have access to me whenever you want. So feel free to use my email address. If you're studying and you're stuck on a question or whatever it is, don't be shy. Send me an email with a screenshot or whatever it is, and I'll help you out. Okay. Will you be sending answers? 5.4. Now we're going to solve. We're not. We're actually going to continue 5.4 next week. So you'll have all the answers to this. We're going to solve it together.